So let me start with the motivation. So the idea is, so let me, when you BV field theory, there's sort of several ways to do BV formulation. And one is maybe what we call the field theory approach. It's where you start with some action of space-time fields, and then you add fields and anti-fields. So we have some space-time action. And then we add space-time, we add anti-fields. So we get anti-fields plus anti-fields to get a BV action of phi and phi star. So that would be perhaps the standard approach when you're doing field theory. In string theory, it's somewhat reversed in some sense. There, what you do usually is you start with some worksheet. Let's take some Riemann surface with punctures, with a certain number of punctures, and then we attach on this Riemann surface. We add a conformal field theory on this Riemann surface, which allows us to attach Hilbert spaces, or at least vector spaces, to each puncture, which we then generate by suitable vertex operators that are building blocks of this conformal field theory. So let me say there's some Hilbert space attached to this. Let me note it by H maybe. And then this CFT, this gives us some maps. CM in terms of CFT correlation functions, which gives us some maps of H tensor M into the complex numbers. So that's usually the starting point in string theory. And on top of it, typically we have not just vertex operators, but we also have an inner product or an odd symplectic form, omega, which in string theory you can just think of as the two-point function on the sphere. And so then we can write, together with the symplectic form, we can write Cm of a certain number of inputs. We can write it as omega, one input, and then some Lm, or Lm minus 1, I should say. And then these Lm, they satisfy they have the structure of an L-infinity algebra, which in turn one thinks of as being the Taylor expansion, in some sense, around the critical point of a BV vector field. So somehow we start the wrong way around. We start somehow perturbatively. We start with vectors with some Fock space or Hilbert space on which you define a particle, and then you build perturbatively a BV action in this way, which I will describe a little bit later. So I still haven't said how this is related to some space-time action. At the moment, I just have some vector spaces and some maps from these vector spaces into the complex numbers or between these vector spaces. So how do I relate this to a space-time action? So then we define a string field. Yes. You integrate already over, some moduli. So I mean this, okay, here I should perhaps, so what we do is, say, take me simplest example. Let me take a sphere with 4 punctures, just as an example, 4-puncture sphere. And then we can write this as being a sort of fundamental vertex, which has some moduli, maybe M included, plus a combination of 3 spheres, 3-pointed spheres, which you can link by a tube. Like this. And then this would be a quartic vertex, or this will correspond to C4 in my notation, and this would be a C3, and this would be a C3. And the suing procedure, or just a fact that this covers the moduli space of Riemann surfaces, punctured Riemann surfaces exactly once, implies that these maps satisfy the axioms of an L-infinity algebra. So this is somehow induced geometrically. So this part I was not going to describe today, but that is basically how string field theory is built. So now, so I still want to get to some space-time action. So what I do is I define a string field. As some state psi in this vector space, which I attached to this puncture, which is part of the conformal field theory constructions. And then I write this as a expanded in a basis, where this I will be more precise afterwards what I mean by this. And the expansion coefficients, which are taken to be functions on X, so this will be the space-time fields. So this is a basis in H, and then this will be the space-time fields. So it will be graded space of fields. Denoted by this curly F. So as an example, we could say that I can, just as this is already using some details, which I will not use so much afterwards, but just to give an example, let me say that I suppose I want to describe a graviton. So we had this in Chris's talk, we had the graviton, so that we can write this as something like you have, I'll write this alpha twiddle mu, maybe, and then times some h, okay, I should write, let me just write it like this, e to the ipx, e to the ikx, acting on some ground state. So you think of this as the Fock vacuum, and then these are creation operators on this Fock vacuum, and then this describes a plane wave. So this would be the element. This would be, this would be an example of this. Okay, I'm a little bit sloppy here, but this would be phi I, and then this would be maybe an element of this basis. So it's a very sketchy picture, but I just wanted to illustrate a little bit how space-time fields arise in these pictures. So morally, you could say that in string theory, geometry is emergent, because you could say that what you really start with is some vector space together with some coefficient functions or expansion coefficients, and then simply using the conformal field theory, which a priori doesn't necessarily have much to do with space-time, will produce you interaction vertices, or will give you scattering amplitudes of gravitons, for instance, in this way. So morally, you could say in string theory somehow space-time is emergent because you start with some algebra of vertex operators acting on some vector space. So I think I've done my duty. We can now stop because unfortunately, it's not quite that way, because the actual construction, the concrete construction of these maps. So the concrete construction of these maps requires that we define this conformal field theory. So we have to really construct this conformal field theory. That means we have to construct these vertex operators, which I should perhaps put here, some vertex operator which will implement that state, or which will create that state on some reference state, and then I need to define these correlation functions. So I should define, I need the v phi, which is perhaps okay, and then the cm, which depend on this v phi x1, and so on. So, but this construction itself usually requires some extra choices. So say we want perhaps the space-time, so that is the target space of this embedding of this Riemann surface to be, say, 10-dimensional Minkowski space, or typically some geometric background. So the construction itself, the technical element of constructing actually the CFD usually actually requires some geometry. So although morally speaking we can say geometry is emergent, when we actually do the calculations we sort of always actually need to assume already some geometry in order to construct this worldsheet theory properly. So maybe that is what I would like to stress here, is that however concrete construction of, say, the CM of these maps require some background, some typically geometric background, require a choice of some geometric background. So, but now, and then we can still proceed. So what one does is we assume a certain background, say, be this 10-dimensional Minkowski space or something like that, and then we simply expand. We do a perturbative expansion around this, so that's like if we do linearized gravity theory. And what we get is we get an action. We get in this way a space-time action, but after all, these correlation functions or these maps, the CM, will depend, of course. These are multilinear maps, so I should say, I mean, it's obvious, these are multilinear maps. So in the end, they will depend multilinearly on this phi, so you can think of them as defining interaction vertices of some space-time action. So we'll write something like omega psi q psi plus 1 over 3 plus factorial omega psi L3 L2 psi plus and so on. So once we have constructed this, we can perturbatively build a sort of polynomial or possibly non-polynomial in the sense that it might be infinitely polynomial of infinite degree, but we can construct perturbatively such an action. So that is more or less the state of string field theory. Fine. So now, however, since in this workshop we're supposed to talk about emergence of geometry, I would like to get rid of this assumption. So I would like to get rid of the background geometry. Now, in string theory, not entirely clear to me how this can be done, not even entirely obvious to me that it can be done at all, but let me therefore take a simpler model. I will therefore today, that is motivates the title of my talk, I will, instead of considering the string theory, will consider the relativistic particle or the word line for which this construction can be done in a background-independent way, and nevertheless, as I will argue, shares many of the essential features that we would have expected from string theory. So then we consider this toy model. So we just consider, instead of a string, some relativistic particle. It's the spinning word line or the spinning relativistic particle, for which I can write down a word line action or a geodesic action. However, I use the Hamiltonian formulation, which turns out to be more suitable for this kind of description. So I write as a PDX. And now, so that would be just, so the embedding coordinate x, and then p is the canonically conjugate momentum. And then I have, since it's spinning, means I assume that there's a superpartner attached to this x, so there's a word line supersymmetry. So I have not just an even coordinate, but also I have an odd coordinate. So I will add a term. Actually, let me also add one more term right away. Probably e over 2 p squared, and then plus a theta bar d theta plus theta d theta bar. So this would be the embedding coordinates canonically conjugate momentum. This would be fermionic coordinates with a vector index, nevertheless. So I should put here an inner product. And then this would be, so if this would be just the bosonic or the normal relativistic particle, and this is the supersymmetric version thereof, if you wish. And dimension I haven't fixed for the moment, so it could be any. In fact, in this talk, it doesn't really matter what the dimension is. But, so let's say any. So, okay, let's say the X is some map from R into Mn. Oh, the theta's have a, you see, this, say, let's put here, put an X mu, and for the theta's, they also have a vector index. So they're word line spinners, so to say. They are not space-time spinners. Yeah, thank you for the question, it's important. Okay, now of course you might say here already you broke your promise, because at the very moment you write something like a p squared, of course p squared you have to first define, so I should really say this is equal to g minus 1 pp, which already depends on the metric of the target space. However, we will get rid of it in due time. For the moment, let it be there without any assumptions on it, but of course, it's still, just by being there, it's already no longer emergent, but in the end, I will emerge it. So at the moment, I'll keep it there, but I will get rid of it eventually. So this, as I said, these coordinates would be Grassmann odd. And then these would be the Grassmann even ones. Now, so this has a super reparameterization invariance. Super reparameterization invariance, so say, so if I introduce some parameter on this word line, say, suppose I take it to be tau to be some parameterization. So if I take a delta tau to be some function epsilon of tau, or maybe, yeah, I think it's fine for now. So then we have this, the invariance is that the delta x is equal to epsilon times p. Then the delta E I will describe in a moment what it is. Delta E is d of epsilon E. And then, so that would be the reparameterization. Then if I do a super reparameterization, I would also have a delta theta, which is equal to some, say, kappa, an odd reparameterization times p, and delta theta bar, I would have, so these would be even functions on the word line, and these would be odd functions on the word line, or vector fields, rather, on the word line. And what's left is, I think that's it at the moment. So here, this is not quite complete as I wrote it. It's not quite complete in the sense that we see we needed this auxiliary field E, so which is just a Lagrange multiplier field, or a gauge field if you wish, for the reparameterizations which I needed to introduce in order for this symmetry to be there. And the same is true for the super reparameterizations. I need to add gauge fields or Lagrange multipliers q bar plus chi bar q, where q is equal to p times theta, and q bar is equal to p times theta bar. So this together with, I'll get rid of this, p squared, these are the generators, these are in the Hamiltonian formulation, these generate this reparameterization, so they are the constraints. Which arise from the redundancy in the description of this word line. So then what we do, I'm sorry? The supersymmetry is here. This is the local supersymmetry, is that you see the delta theta is kappa p. And oh, I forgot something also, but actually, delta, sorry, this I think looks actually wrong. Let me fix it. So maybe I have it right. So delta x is kappa p, kappa theta, right? And delta theta is kappa p, kappa bar p. So I think delta theta is kappa t. So then it's p. So now, so thank you for pointing out. So it wasn't complete. I only wrote half of the supersymmetry, word-line supersymmetry. Thank you. So now we have this constraint system. So if we want to quantize this word line, we have to quantize this constraint system. So what we do is we do the BRST quantization of this of the word line theory. So we do the usual rules of BRST. We associate to each constraint will come with a ghost. So we enlarge the number of space-time fields get enlarged by what? So we get pairs. We get the x and the p. As pairs, we have then the theta bar. We have the c and b. C is the ghost for the reparameterization. So, or for that, and the B is the anti-ghost that goes for it. And then since I have super reparameterization, I also introduce a pair of super ghosts, which I'll denote by gamma and beta bar, and also gamma bar and beta accordingly. So this is the content, if you wish, the operator content of the BRST quantization of that word line. So, and then, yeah, so now we want the constraints to close. So the closure of the constraints will mean that we can define a BRST operator which is squared to 0. So we can build out of these constraints a BRST operator, QBRST, which I write as just a minus C P squared. So I have the ghost for the reparameterization constraint goes with the reparameterization constraints plus the super ghost that goes with the Q bar plus gamma bar that goes with the Q. And then you have the structure constants which go with gamma bar. So that would be the BRST operator. And this squaring to 0, okay, I will no longer write, I just write it as Q. And then Q squares to 0 means what? Means that the constraints close. Of course, this implies the closure of the constraint algebra. But it also means that, in fact, the physical particle, so the physical maybe particle that is described by this word line is described by the cohomology of Q. So if Q squares to 0, I have a cohomological problem, and therefore in the cohomology of Q are the physical states that are propagated by this word line. So that is the usual content of BRST quantization. So I'm not doing anything too exotic. So it just means we now have identified a quantum particle that is indeed propagated. We have to still find out what particle this is, but maybe it's nothing interesting, maybe something interesting that we'll have to see. But what I wanted to point out is that this construction so far, although in this p squared at the moment, I will get rid of it eventually, but at the moment, although this p squared involves some background metric, the construction is completely independent of any choice of background metric. In contrast to string theory, where I don't have that luxury, where I usually need to choose a background in order to construct the Virasoro algebra or the BRST operator. All right, so maybe here I should see if there are any more comments or questions about what I've done so far. So if you wish, this is just a review of word line quantization of the spinning particle. So now, what I want to do, since I want to emerge things, I want to forget about the word line. I want to forget what I've done. I want to do what I can do very well as age proceeds, forget what you've done in the past, and just remember what's left, right? Just look at what's left and say, oh, this is fantastic. So what I see, I have an algebra. Obviously, I should impose, I mean, if I, yeah, let me write that perhaps here. I will say, let me forget where all this comes from, and I just look at this blackboard, and then I see apparently I have here just some graded algebra, or some graded superalgebra. Yes, please.
This methodology that you just described, it's what? Constraint set?
Okay. Okay, that is very good. That is actually good. Is a very good comment. It's of course the Q has sort of two natures. It has on the one hand it encodes the constraints. So the Q squaring to 0 means that the constraint algebra closes, but closes on what? Actually, because you can also say the Q is not just an operator. Of course, you can think of it as a Lie algebra element. Then Q squared is a graded commutator, but you can also think of it as an operator that acts on something. And indeed, that is very important. It will play an important role, is that we want to think of Q as acting on something, so Q as an operator on vector space, and then the particles will be sitting in the cohomology of Q as an action on this vector space, which will be this space H, which I introduced before.
Okay, so this doesn't see the rest of the equations of force, only sees.
Right, so that's what we then eventually will see some of the linearized equations of motion. But yeah, this we will have in some more detail in a little bit. So, but now, before I do that, yes? Yes. On the representation space. Absolutely, yeah. So I should perhaps put here cohomology on Q on this representation space. Yeah, indeed, BFV. Okay, so now but first, before becoming more concrete again, I want to now be forgetful and say the only thing now I remember is that for some reason I am given this algebra, which I can think of it as a Lie algebra. In fact, this turns out to be later an associative algebra, but let me call this the algebraic formulation. This is what I learned from Maxime. He very kindly explained this to me a few years ago. That was content of a paper we then wrote together. So let me write with Grigoriev and Adiel Meyer. So what I'm saying then is, okay, let me just say, suppose I'm just given some graded algebra. Possibly Lie. I mean, Lie for sure, because this satisfies some commutation relations. So this will be equal to perhaps I H bar. H bar we can set equal to 1. This will be equal to 1. This anti-commutator will be equal to 1. Here is a commutator. These are super ghosts. Will be equal to perhaps -1. And this, I take it to be equal to 1. And so I'm given actually, through the BRST quantization of the word line, it has given me a Lie algebra. And then I can say, okay, suppose I'm just given a Lie algebra with a basis, again, EI, homogeneous basis. Also homogeneous degree. So, and then, so I can say, let me forget everything else, let me just suppose. So for some reason I'm given a graded algebra, and I want to see, can I build a dynamical system out of this, out of which geometry emerges? So let's do that. So let's try. So what I'm going to do is I'm going to take, of course, since being a graded algebra, you will have elements in all degrees potentially, or in many degrees, but I'm going to pick out a particular degree. I'm going to pick out some Q of phi, which I'm expanding, so it's a linear space, Again, this is my basis in the algebra. It could be any of these objects, or in fact, potentially combinations thereof. So I'm actually going to use this as an associative algebra, as you will see. So again, this will be my space-time fields. So what I'm doing, actually I'm cheating a little bit. What I'm doing, I'm taking one of these generators of this algebra. I'm taking it as I'm considering functions rather than polynomials of this one generator. So I'm considering functions of this generator. So I put this here, and then the EIs are the rest. Polynomials, therefore. So, and then I want this to be of ghost degree 1. That's my only restriction at the moment. That is some element of here. Okay, which I expand. So then, given this structure, I can already construct a homological vector field, or a BV vector field, in space-time, simply by doing the following instruction. So I'm going to define some homological vector field on the space of fields, which I denoted by F previously, simply by saying that S of phi I contracted with EI is defined as being the gradient commutator. So since I used anti-commutator, I should do that here as well. Q of phi. So you give me a phi, a space-time field phi here, or a set of space-time field. I read off what is Q of phi simply by this prescription. I take the gradient anti-commutator of this, and then I read off what's the result, and then I define this to be the action of this PV vector field on the space-time field phi. So it's clearly homological because of Jacobi identity. So S squared equal to 0 because of simply the Jacobi identity of the bracket, of the odd. So this is a very simple way to construct a homological vector field. Now, of course, once you have a homological vector field, if you think of the geometric construction of PV, then you think of, well, let's look for the critical points, because the critical points of PV vector fields are supposed to be the solution of the classical equations of motion. Right? So if you remember when you do, I've deleted this part, but I'll just recall, in field theory, we would say S would be the anti-bracket of the BV action with whatever field you act on. Yes, please. Yeah, it's just Chevalier-Heisenberg, just for an infinite dimensional version. Yeah, nothing more. So now I will say, if I remember that in field theory, usually we define this BV vector field as being the BV, the anti-bracket of the BV action with whatever you act on. Then we know that the critical points are, okay, I'll just write this as maybe omega, what is it? IV of omega, if you have a symplectic form, or how should I write it? Yeah, if you have a symplectic form. So what I want to say is that the, or maybe better to write it as, if it's Hamiltonian of ds. Right? So then we see that the critical points of the BV vector field are, of course, when the first variation of the action vanishes, which are the solutions of the equations of motion. So then we can say, okay, let's look for the solutions of the equation of motion, is whenever this vanishes. Which is then we fall back on our situation which we had here, say, well, that is indeed when a particle can propagate. So when this Q squares to 0, that means this word line is actually a particle of sorts. It can propagate. So that makes sense. So that is very much what one does in string theory. Only in string theory one doesn't do it that way because we don't really know how to do this construction explicitly, although sort of morally speaking, that's what one would do if one could. So, okay, so then we can say Q squared, so S, the critical points, the point phi star is when Q of phi star squares to 0. All right, so now, still, I have lost in my sort of process of abstraction. You know, abstraction, so what I've done is I've said, okay, I've forgotten where I came from. I just, for some reason, I was given this algebra. I created this thing, which seems to describe some equations of motion, but what is the particle that I'm describing? So for this, what I'm going to do is I'm going to say, okay, let's try to see, can we identify, because if I wasn't starting with a particular word line, but just some algebra, I have no idea what particle I'm describing. I just know I have some algebra of generators, but I don't know what it describes. So then, we'll try to go, we need one more ingredient, which in string theory would be called an operator state correspondence. That is what we do, is we say, okay, let's say this is our space of field, and I have found some critical point, star. So this is some solution of this. So these are just some background fields at the moment. So then I can say, let's look at the tangent space T at T phi star of F. So let's take some vector. I'll denote it by delta phi. It's a small variation. So I say phi is equal to phi star plus delta phi, small variation. So can I associate an element in a Hilbert space to this thing? And what I can do is, so I would like to have a map from this phi to something in H, and that would be what we call the operator state correspondence. Operator state correspondence. And what I want to do is I simply take the variation. So let's say I take this is mapped to some psi, which is an element in H, and psi is given by the variation of Q. So you see Q depends on phi. So I take Q at phi star, I vary a little bit phi star. As a result, Q varies, and I act with this on some reference state, which is an element in here. So I take some element, some reference state, it's like you call it a Fock vacuum, if you wish, some vacuum state in H, you act with delta Q on it, and then you say, this is my state. So this is something I learned from Warren Siegel. That is this idea. So now it's clear that if omega is an invariant state, so you want omega to be Q invariant. So Q star, let me call it Q star or Q phi star. If omega is Q invariant, then this construction gives you an element in the cohomology because I mean, if Q squares to 0, yeah, and so on. So you get so basically what you're saying is you're asking, you take a solution of the linearized equation. Remember, phi star equals 0. Q squared equals 0. Phi star means the equation, the action as a stationary point. As the first derivative vanishes, and then you ask for what about the second derivative? That's the variation around this point, and these are the linear excitations. So, if you expand Q of phi star plus delta phi, Q of phi star plus delta phi, you expand it to first order, you get precisely the condition. So you impose this equal to 0, then this will tell you that Q of phi star, phi star, can do it, with delta Q equal to 0, and then if you act to this on this state, it gives the element in the cohomology. So now we know, if you tell me what is my set of background fields, I tell you what are the types of particles you describe by simply acting with the delta Q on some ground state, if you wish. Okay, so this map, however, is surjective, it's not injective. It's surjective, so to say, almost by construction, because every element in H is obtained in this way. But the fact that it's not injective will gives rise to some ambiguities, which can cause problems, but we'll see that. So that's the general structure. So I would just like to repeat. So you give me an algebra, a graded algebra. I produce an element, I take an element of goes degree 1 in this algebra. Most general one, I describe it by some graded coordinates. And then I'll give you a space-time field theory from it. Now, of course, a priori, you don't know what this field theory is. It's some BV field theory, but it might be completely useless, uninteresting, or maybe interesting. So this is still to be seen. But it is emerging. So at the moment is no geometry, of course. I'm just saying fields. Does it have anything to do with geometry? We will see. It depends on the algebra you choose, whether it has anything to do with geometry or not. But it is an emerging field theory out of just algebraic data. So that's the point I wanted to make here. So now what I want to do is I want to just discuss some examples. So in the rest of the talk, I will discuss a couple examples and to see what kind of field theories or geometries you get out of this construction. So example. So the first. So now I have to make a choice. I take this algebra that I was given. I take this algebra, since it's a nice algebra, and I take H, which I define to be H1 for a good reason. I just take it to be polynomials with coefficients in C infinity functions of half of my generators. And did I forget C? So if you look at my algebra, I took, like in quantum mechanics, I took X is part of the coefficient functions. I took theta, C, gamma, and beta, but not the Barth fields. So the Barth fields are the canonical momentum conjugate. And that's like in quantum mechanics, we don't write the wave function as a function of X and P, but just of X. So I'll do the same. So these are my wave functions. Okay. So I wanted to put here like this. Okay, and now what is this H1? So the thing is, this is still a very big space, in fact. There's an infinite dimensional. It's a little bit too big. So what I'm going to do is I'm going to use a fact that there is a natural U1 action on this algebra. That is, I take this one, there's a U, okay, so I say that there is a U1 action, which we call R symmetry in terms of supersymmetry. That is, I can rotate this by e to the I alpha, e to the minus I alpha. This also gets an e to the I alpha, e to the minus I alpha. You see all the Barth coordinates get a minus I alpha, e to the I alpha. These don't transform. Those who don't have bars, they don't transform at all. So then I can say, so I have a current or a charge associated, a Noether charge associated with this transformation, so and I can say I'm only looking at elements in this vector space which have Noether charge 1 with respect to this U1 action. This is a restriction which is compatible with the operator. So then let's do that. So that's just a way to reduce, the system is reducible. Okay, so I'll do that. Then, let me see. Now, I'm going to go back here and say, okay, what is the general set of background fields I can introduce within this setting? So here I'm going to be a little bit short. I'm not going to explain everything in enough detail, but I hope you will trust me that it's meaningful. So I'm going to write this as minus C, and then as we had already, I'm going to write the G minus 1 nabla nabla, where I think of this at the moment as some covariant derivatives with respect to some connections, which I will perhaps explain in a little bit. I could also add some object which I denote by G3, which is nabla, 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 with 3 nablas, why not? And so on. So this is still all possible because compatible with my U1 charge, because none of these things transform. You see the C doesn't transform, the nabla doesn't transform, so I can write down a lot of things. However, so this is already annoying. So I see that, in fact, it's still too big. So the space of background fields is still infinite dimensional because I could put not just p squared, but p cubed, p to the 4, p to the 276. So this will be interesting if you want to perhaps discuss higher spin fields, but suppose we don't want to discuss higher spin fields. Then I'll say, okay, let me see if I can reduce the space even further. What I'm going to do is I'm going to introduce an extra grading, under which this will have grading 0, this will have 1, this will have 1/2, 1/2, -1, 2, 1/2, and -1/2. This will have 3/2. Those of you familiar with string theory, of course, immediately see the conformal weight of these fields. But I can also do it if I don't know about string theory. I can just guess these gradings. But of course, I had learned a little bit of string theory before that we came to these gradings. But let me just add this grading. So then I can introduce a filtration with respect to this grading. I need to do filtration because Lie brackets, they can reduce the grade. Say, if I have a p with, for instance, if I take the Lie bracket of x with p, I get a 1, which is grading 0. So I take a filtration. So what I can do is I can filtrate this BRSD operator, and I can say, okay, let me stick to a certain filtration. Say, in this case, I take filtration 1. You say a filtration 1. Then this is because it has already 3 p's. Together with a -1 here, there will be already a 2. So this will be excluded, and all the higher spin, so to say, background fields will be thrown out by this filtration. Not necessarily something you have to do, but let's do it. I want to reduce the system to something manageable. Okay, so now it becomes smaller. Still, though, I can add extra terms. I can add something like an F2, a 2 form, and then contract it with these theta's. And I can add another tensor 1, 3, which has the sort of algebraic symmetries of a Riemann tensor, theta, theta bar, theta, theta bar. I could add some auxiliary fields. I can add gamma, and then I have this theta, what did I have? Mu, I can put here a nabla mu, where, or let me not put mu, let me just put inner product, where this, I can put some spin connection, possibly U1 connection, and I should put a bar, and then gamma bar theta, again, with spin and U1 connection, and if I do it here, I should probably allow for it here also. So all sorts of connections. I just add everything I can add, which within this filtration. And then you may ask, okay, let's add within this filtration 1, let me add all the possible background fields which I can, and let me again ask what are the critical points? What will I get? Do I get something that I recognize? So if I do that, so then I look what is phi star, so I'm looking for the nilpotence condition of Q, and there's a little, how to say, I cheat a tiny little bit in the sense that there seems to be a dilaton floating around here that I will just ignore for the moment, but other than that, it's complete, is that I will get the condition that, that dE, where E is the Vierbein that enters in this metric, plus omega, which E is equal to 0, so I get the torsion condition, and I get that F, this F2, this 2 form, has to be the curvature of the A connection. So F has to be, so to say, curvature. I just write curvature of A. I find that the R13 has to be the Riemann tensor of the spin connection. And I also find that nabla F equal to 0. So these are the conditions that you get. So initially these things were independent objects which I have allowed as background fields, because remember, we started with a linear space of background fields. There was no condition between F and, say, this connection. But the fact of being on a critical point makes a connection between. It says F2 actually has to be the curvature of this U1 or SU2 non-abelian connection. And here you get the Yang-Mills equation of motion. So to summarize, what we get is Yang-Mills emerges in this theory from the algebraic data that we imposed. We also get a torsion-free connection, but we do not get Einstein equation. It just tells us the Riemann tensor is the Riemann tensor of that metric, but it doesn't tell me it doesn't give me any Einstein equation. So gravity is, so to say, off shell. And also, but it gives me some conditions. So now we've identified the field theory that we have built out of this algebraic data. Now, so it's still not quite perhaps geometry, but it's coming closer. This may be, I will skip. So I just would like to mention at this point that I could have, what I took this Hilbert space to be polynomials in beta and gamma, but this algebra, this Weil algebra, has another representation. It has these polynomials, but it also has another inequivalent representation. Perhaps put here. By the way, here, yeah, that's fine. So this has another inequivalent representation where I take H1, or H rather, to be, again, C infinity. But now I take gamma bar and perhaps C, and then acting on delta of beta. And this is another, what we call picture one representation. And again, if you look at sort of the cohomology, you'll be, what you find is that psi is equal to 0 delta beta plus A1, one form, delta 1, first derivative of beta, plus 2 form, second derivative of beta, and so on. And the Q acts like this. So that's the action of Q. So the Q acts as the exterior differential. So what you get actually in this way, you don't get Yang-Mills theory, but instead what you get Chern-Simons theory. This is probably something which we are discussing with Boffo, Grassi, and Hulik. So you could do more, or you could say, assume that actually the target space has some complex structure. If you add in a complex structure in target space, and you say that these A's are not Lie algebra valued, but you take them to be taking values. So you take A to be element of omega with values in the tangent space, then you get the B-model topological string. So that's not too surprising, because the B model is really a point particle model. It's not really a string theory because localization. So in a way, I'm not too surprised. But this goes another application of this formula. So now let me go on. So that was just to see a little bit what you get out of that type of algebras. In fact, for this B-model topological string, there has been a paper in, I think, 94 or so by Marcus and Jankiewicz, which also, I think, is essentially, that's also there. All right. Okay, so now the next, let me see, I have 5 more minutes if I'm correct. 6 or 7, very good. So I have to come to the punchline because I'm still haven't quite emerged the geometry, but let me go a little bit further. So what I'm going to do is I'm going to enlarge a little bit my algebra. So let me assume that these odd generators, they have an extra index. Put here an I, and here an I. And I is equal 1 or 2. And then the same here, of course. Then this has an I, and this has an I, this has an I, this has an I. So that just means I take the word line with non-minimal supersymmetry. I take n equal 4 supersymmetry on the word line, if you want to think. So again, of course, although I could say, you're a genius, you're thinking of all these algebras, of course I'm not. I'm just taking models that you already know, and I interpret them. Although one is not necessarily forced to do that. So now, what happens when you do that? You see, before, remember when we discussed Yang-Mills theory, we said, well, we get maybe that the curvature has to be the Riemann curvature of this R, but we didn't get any equation of motion for the metric. Now you do get an equation of the metric, and also you'll find that the delta Q acting on some ground state will give you, now for a suitable deformation, let's say this is my delta phi, will give you the graviton. So then what one learns is in the n equal 4 theory, actually, you describe a graviton, and in fact also a Kalb-Ramond field, and also a dilaton. There is a little hitch, though, with this omega is, it's a little bit more special in a way. So the omega is really, the state omega, this sort of reference or ground state is really, I should write it as psi mu, theta 1 mu, beta 2. So this is already a bit technical, but so psi mu is some vector field, or some one form, and so theta mu is this thing. So what I'm trying to say is, oh, this is totally anti-symmetrization, this is 1 and 2. So what you do is this omega already picks out some direction in space-time. So Lorentz invariant, this thing is not Lorentz invariant, so to say. And so you pick out some distinguished vector. I will come back to that a little bit before. That's probably for somebody who knows string theory, so then that's where you fail, because in string theory we don't have to do that. In string theory we just say the graviton is vertex operator is something like vertex operator times means loosely speaking vertex operator times vertex operator twiddle on the ground state. We don't have to pick a sort of a polarization here. So, but you see, we cannot do that. We don't have vertex operator. We have to write this thing as delta Q of something. Now, delta Q has Gauss degree 1. I want to get something in Gauss degree 0, so this thing has to have Gauss degree -1. And that is where I'm forced to make this compromise. However, I will argue later that it's not really a weakness. So, but I'll come to that in the last 2 minutes. Anyway, but so we'll see if in this theory now, you actually will propagate the graviton. And if you ask what is phi star, so the critical point of this homological vector field which you constructed, it will give you indeed what people often call the n equals 0 supergravity equations of motion. So you get the equation of motion for the Einstein-Dilaton Kalb-Ramond field, which again, perhaps at the end of the day, you say, perhaps shouldn't be too surprised, because in the alpha prime going to 0 limit, the string becomes a point particle. So that's just what we find. But of course, in string theory, usually that's the backgrounds we're looking at are those which survive in the alpha prime going to 0 limit, because we don't have any string modes excited, massive string modes excited. So we might have a start with that. So now, in the last minute, I want to really emerge the geometry. So what I'm going to do, I'm going to take this algebra, and I'm going to look again at this operator. So let me simplify it a little. Let me remove some of the stuff here that's just obscuring a little bit the structure. Let me remove that and just stick to these two things. So when I see what these are, let me write, what is this? This is equal to, I can write this as Minkowski metric if I like, AB, and then EA mu, EB nu, nabla mu, nabla nu. I just use Minkowski and then some Vierbeins. And here is the same. In here I have what, if I look at it? It's a theta A. So I can take to have a tangent space index. And then what is written here is an EA mu nabla mu, this thing. This thing is the same as that. So now, let me do something crazy. Let me set them equal to 0. Why not? So what's left of my BRST charge? What's left of my BRST charge is this. B gamma gamma bar. We say, okay, that's the vacuum BRST charge, no metric. So I'll get rid of the metric and say, okay, well, if it's not illegal to do, I can always do it. And I think actually Chris and Nathan Berkowitz, I think you also played once with such things. No, I think I'm not original in that sense. So then let me take, so I take Q0 to just B gamma gamma bar, and let me say what is the cohomology of this thing. Now what you find, of course the algebra hasn't changed. The algebra is still the same. The vector space is still the same. So when I look at the cohomology, by the way, here I forgot to say that was with Roberto Bonezzi and Adil Meyer. So here then I look, what is the cohomology of Q0? And if I look at it, I will get psi as an element in there. So it has to form some HAB. I'll just write it like that. Theta 1A, theta 2B. This is now a little bit technical, but I hope you'll forgive me. Gamma 1, beta 2, totally antisymmetrized. So HAB are just some scalar fields. There's a bunch of scalar fields here, and this is some also scalar fields, and they contract these tangent indices, if you want. H is just some function. Just some function is just a function. Not related to HAB any. And indeed, you can, again, you have an operator state correspondence. I can write this state psi. It is equal to delta Q of acting on the ground state, which is the same ground state as we have before, the one up there, and psi. Let me put maybe psi. So the way I get it is simply by acting. What I do is for my delta Q, let me write it down here, I now take delta Q. So Q0 is this, and delta Q is equal to gamma bar theta A EA plus omega A B C theta B theta bar C. And omega EA, and are just some fields, that's just some connections, if you wish. No, they're not vector fields, they're just functions. And so they will generate, if I act with this on this, they will generate this thing. So I have an operator state correspondence. So that means I have now identified in my space of fields, I've identified a phi star, which is no metric, but I have a space but no metric. And I've identified a tangent space, delta phi, and the tangent space is, through the operator state correspondence, is related to this. So these are my particles, if you wish, but nothing propagates, of course, because there's no derivatives. So now I'll say, okay, let me see, is this a tangent space, is this a tangent vector to a curve of Maurer-Cartan elements? You know, so I found one point, but can I continue that linear deformation to a finite deformation? For this I need to solve, as before, as always, Q phi squares to 0. Right? I need to solve this equation. If I can, I know it's true at this point where there's none of these fields are turned on. If I go away, the linearized equation is the cohomology is there, but let's look at the nonlinear equation. And what you find is this implies, and I'm almost finished, EA, EB cannot commute. So linearly, at the linear you have no conditions on EA, B, but at the nonlinear level you find that the EA and EB cannot commute. So they cannot be functions. Now you can do two things, or you can do several things. So you could probably make a matrix valued. Some people might like that. But I chose to make them vector fields. Now if you make it a vector field, you're back here. And immediately then, in that case, immediately the nilpotency tells you that the metric has to be Einstein. So basically, the moment you try to go away from here, you have to make this E's non-abelian, make it either by making matrix valued or vector field valued. If you choose the vector field, you have space-time, you have a metric. So now the geometry has emerged. And probably that's a good time to stop.
Thank you very much. That's very nice talk. Are there questions on it?
Yes, Anton.
Yeah, I have a question which I'm not sure, maybe it's somewhat misplaced. But so you explained how the ordinary differential geometry is related to this stuff. Could you imagine doing the same with generalized geometry?
It's very interesting. We just had this discussion with Maxime today. It seems there should be a pretty close relation of what we're doing here with generalized geometry. I think.
What would you need to change? Do you need to add more fields, or with the same fields you would just consider more general combinations?
For me, it's a bit the question premature, but because I missed Peter Schupp's talk, but Peter Schupp was here earlier this week, and I think he seemed to argue that somehow these same objects appear just in generalized geometry. And so maybe one just has to identify, but I haven't looked at it. So that would be, unfortunately, I missed that talk.
So I think we've had this conversation before. I was looking just at the bare spinning particle
Right.
and found all this, what I thought was pathological homology classes.
In negative degree.
In negative degree. I'm wondering if there, can you interpret them in this way?
Well, I don't know. I mean, my suspicion is, again, actually here I draw on discussion with Maxim also, that these will be, how to say, they will not show up in the physical.
Yeah.
So they will be there in some off-shell gauge symmetries or so, but they will not show up in the physical sector. That is my suspicion. So that's all I can say at the moment. Yeah, but it's indeed something we should look into. That would be something we should do. Yeah.
Maybe let's postpone further question and discussion to the coffee break, and we reconvene at